Hi, my name is Lori, and I'm a support engineer with GEO-SLOPE. I've created a series of getting started tutorials for new users to GeoStudio. So if you're brand new to using the GeoStudio software and you're not quite sure where to start, then you've come to the right place. These tutorial videos have been designed to help walk you through the basic steps of creating a simple model using GeoStudio. The main topics that will be covered in this series will be how to use define to set up a numerical model, using the solve module to compute the numerical solution, and how to use contour to view the results and to gain a deeper understanding of the problem you're modeling. You can pause, stop, fast forward, or rewind these videos at any time by using the controller bar positioned at the bottom of the window. If English is not your first language, you might find it helpful to print out a copy of my script, which is available as a PDF from our website. So let's get started. The QUAKE tutorial presents the step-by-step procedures involved in creating a simple earthquake analysis. The objective of the QUAKE tutorial is to look at the dynamic response of an embankment on a loose soil deposit in terms of the motion that will occur at the crest of the embankment during the earthquake event, and to estimate the excess pore-water pressures that may develop in the loose foundation soil. Here is a schematic diagram of the problem. Both the embankment and the foundation soil are linear elastic soils with slightly different unit weights, but the same Poisson's ratio of 0.334 and a Gmax value of 5,000 kPa. A damping ratio of 0.1 will be applied to both soils. The pore water pressures are only going to be considered in the foundation soil. The weight of the water will be modeled as a fluid pressure boundary condition on both soils, and the underdrain that exists at the toe of the embankment is considered in the analysis only by the way it controls how the phreatic surface is drawn. The earthquake record, which is included in the example folder of GeoStudio 2007, has a peak acceleration of about 0.35 g. However, the peak acceleration of the earthquake at the site we are modeling is considerably less at 0.12 g, so the record will need to be modified for this analysis. We start by creating a new QUAKE project from the Start page of GeoStudio. When the Key in Analyses dialog box appears, select what type of analysis you're going to do and give it a name and description. The QUAKE tutorial will actually consist of two separate analyses. Let's first create the in-situ static analysis to determine the stress state conditions that exist before the earthquake occurs. The pore water pressure conditions will be determined from the initial water table that we define. The first time you start working with GeoStudio, it's helpful to learn what different toolbars exist. Many of the drop-down commands are also available as individual icons on the many different toolbars. You can familiarize yourself with the toolbars by toggling them on and off. When developing a numerical model, the first step is usually to set the working area, which defines the size of the space available. The working area may be smaller, equal to, or greater than the printer page. The next step is to set the scale. The scale should be set such that the minimum and maximum extents match those required for the analysis. Define the X and Y extents to find an approximate scale and then fine-tune it so you have a 1:1 aspect ratio. A background grid of points will help you draw the problem. And it's always a good idea to save your file frequently. It's often helpful to sketch an axis. Before you start, click the Zoom page icon so you can view the entire working area. Then choose Axis from the Sketch menu. The axis is drawn by moving the cursor from the bottom left corner and stretching it outward. The number of increments can be adjusted using the Set Axis drop-down menu. Before defining the geometry in QUAKE-W, it's convenient to first sketch the problem. select Polylines from the Sketch menu. Use the cursor like a pencil. Click the left mouse button to create a series of lines. The lines are considered objects which can be adjusted or deleted using the Modify Objects command. Text can be included in the profile by using Sketch Text. Use the cursor to place the text on the profile. The approach to use when developing a numerical model is to draw the geometry, create and assign materials, create and assign boundary conditions, and then finally review and fine-tune the finite element mesh. Let's start by drawing the geometry. Individual soil regions are created using the Draw Regions command. Click the left mouse button to create region points. Once the polygon region has been closed, you can either continue to draw additional regions, or you can right-click the mouse to exit Draw Regions mode. Materials are first created and then assigned to geometry objects. Choose Materials from the Draw drop-down menu. Click on Key In to create a material. Add a new material, name it, and select the material model from the drop-down list. For this case, we will be using a linear elastic model for the embankment material. The two most important soil properties required for the initial static analysis are the total weight of the material and Poisson's ratio. Poisson's ratio is important because it influences K0, the coefficient of earth pressure at rest. We will also input a damping ratio and Gmax value. To create the second material, you have options. You can either add or define a second material as we did the first, or you can clone an existing material since they're similar. Even though excess pore water pressures will not develop during the in-situ analysis, we want to model the generation of excess pore water pressures for the dynamic analysis. Therefore, in the foundation material, we need to define a minimum of two functions. They are called the pore-water pressure ratio function and the cyclic number function. For this example, we can use the sample functions, which are included with the software. Watch how these functions are created and then assigned to the material. The materials can now be assigned to the individual geometry regions. To establish the initial pore water pressure conditions, choose Initial Water Table from the Draw menu. The default maximum negative pressure head that will develop above the water table is set to be 5 meters. Draw the water table on the profile. Boundary conditions are created and assigned in the same way materials are. Select Boundary Conditions from the Draw menu. You can also create your own boundary condition by clicking on the Add button. For this example, we need a boundary condition that will reflect the pressure of the water reservoir that exists at an elevation of 12 meters. Once the boundary conditions have been created, you can then apply them to the region geometry. Along both the left and right vertical boundaries, the soil can't move in the x direction, but it's free to settle in the y direction. Along the bottom, we're going to assume the movement is fixed in both the x and y directions. Boundary conditions can be applied to region edges, region nodes, region faces, free lines, or free points. Now that the geometry has been drawn, the material properties have been created and assigned, and the boundary conditions applied, it's time to review the finite element mesh and make any necessary adjustments. You can view the finite element mesh using Draw Mesh Properties. The meshing algorithm in QUAKE-W is defaulted to use a global element size. For this simulation, a global element size of 1 meter is adequate. The finite element mesh will disappear after you leave the Draw Mesh Properties view. If you want to leave it on, you can click the View Mesh icon on the View Preferences toolbar. We've finished the problem definition, and now it's time to verify the analysis. The solver for QUAKE-W can be launched by clicking on the Solve icon. Click the Start button to activate the solver. You can view the results directly by clicking on the contour icon in the Analysis toolbar. By default, Y total stress contours are shown, which can be labeled using Draw Contour Labels. Since the dynamic analysis is going to use the results obtained from the initial static analysis, it's important to ensure that the initial conditions are reasonable and realistic. Notice how the total stresses under the reservoir, where the ground is horizontal, are about 40 kPa. This represents the 4 meters of water level in the reservoir. By default, pore water pressure contours can also be viewed using the drop-down list. Effective vertical stress contours can be created using Draw Contours. Up to this point, we have computed the initial in-situ static stress conditions and the initial pore water pressure conditions, and we've reviewed the total and effective vertical stresses. These results represent the initial conditions that will be used as the starting point for the dynamic analysis. To create additional analyses, return to the Define view by clicking on the pencil icon. Click on the Analyses icon or use Key-in Analyses. To add another analysis to this project, you can either add it from the drop-down list, or you can clone an existing analysis. Since we want to use the same material properties as what we used before, we should clone the in-situ analysis. Geometry is considered specific to the project file. The second analysis will be an equivalent linear dynamic analysis that will subject the profile to the earthquake event. This second analysis will use the results from the first one as a starting point. In GeoStudio, this means the in-situ analysis will be the parent of the dynamic one for both the pore water pressure conditions and the initial stress conditions. Since the dynamic analysis is time-dependent, we need to define time steps that are appropriate for the earthquake record we're going to use. First, let's import the earthquake record into GeoStudio. Go under the Time tab and click on the Key-in button. The example record is stored in the GeoStudio 2007 Examples folder. We can import the record and then modify it to have a new peak acceleration of 0.12 g. We will leave the time frame the same at 10 seconds duration. Once we've created the record, we can then return to the Key-in Analyses Time Steps dialog box, and time steps will have been automatically generated from this record. There will be 500 time steps with 0.02 increments and we will save the data every 50 time steps. The boundary conditions applied on the vertical edges of the boundary need to be changed for the dynamic analysis. Previously, we were allowing vertical movement but restricting lateral movement. Now we need to do the opposite. Restrict vertical movement but allow the ground to sway from side to side as the horizontal earthquake accelerations are applied. In addition, the water reservoir stresses can be removed since they're already accounted for in the initial stress distribution. In Quake W, you can select specific points where the results will be saved for each and every time step while integrating through the earthquake record. These points are called history points. Let's define two history points, one at the top of the crest and one at the bottom of the profile. History points must be defined to geometry points, so we'll need to insert a geometry point and then apply the history point to it. Quake W is formulated on the basis of a time integration scheme. This means that Quake W steps through the earthquake record at a specified time interval and does a finite element analysis for each time step. By default, Quake W stores data at the 20 highest peaks in the earthquake record. In addition, it's been specified that the data should be saved every 50th time step. You should be aware that the more time steps you save and the more history points you select to save the motion history at, the larger your file will be. The definition of the dynamic analysis is now complete. Click on the Solve icon. It will take a little while for the program to complete the full 500 time steps. In this simple example, we're only using linear elastic soils, so there are no convergence issues. Before we look at the dynamic analysis results, let's review what we've done and define. We first created an in-situ static analysis that had its own boundary conditions and material properties. We then added a dynamic analysis that used the results from the in-situ static analysis. The dynamic analysis could also have its own material properties and boundary conditions assigned. In this simulation, we only changed the boundary conditions. Let's look at the dynamic analysis results. The vertical effective stress contours will still be showing, but will have updated for the new range of data. We had defined a history point at the crest of the dam and at the base of the problem. In Contour, using the Draw Graph command, we can create graphs specific to the history points where the data was saved for each time step. Let's plot x acceleration versus time. You need to point to the location of the history point that's going to be used to create the graph. Create a clone graph for the other history point. If you hold down the Shift key, you can select multiple graphs to view them at the same time. You can see from the graph that the peak accelerations at the crest reach values greater than 0.3 g. Since the applied peak acceleration was only 0.12 g, this indicates that there is some amplification in the motion at the crest. You can also create graphs of lateral displacement profiles along the center line of the dam. In Quake W, it's important to understand that only relative displacements cause dynamic shear stresses, and only dynamic shear stresses lead to the generation of excess pore water pressures. In Contour, you can also create a movie of the motion. Let's create a movie of displacement relative to the fixed base. First, set the view to show the displacement mesh and define the magnification that you would like included in your movie. Turn off any additional details you don't want included in the movie, such as the axis or any boundary conditions. The movie is created separately from GeoStudio and can be played using Windows Media Player. In an equivalent linear analysis, a key parameter obtained is the cyclic stress ratio, or CSR. This number is used together with the cyclic number function that we created and defined to indicate the possibility of liquefaction. Generally, the higher the CSR is, the higher the possibility of liquefaction. Values greater than about 0.2 in this example indicate liquefaction is possible. You can also show zones of potential liquefaction directly through the View Preferences toolbar. We were interested in excess pore-water pressures that might develop in the loose foundation soil. You can create contours of excess pore-water pressures to reveal that there is a pocket of excess pore-water pressures that exceed 30 kPa in the downstream side of the dam. New to GeoStudio 2007 is a reporting feature. If you need to generate a report of your input, select Report from the View menu. Once you save the report file, your default word processing program will open with a generated report. You can now insert pictures, apply style templates, or add and delete data. If at any time you need help with understanding a dialog box, you can click on the question mark in the top left corner to access the online help, or use F1 on your keyboard. You can also switch to the Analysis Start page, which has PDF copies of all the engineering books for GeoStudio under the Documentation section. These books are very helpful in describing the features in the software and the theory behind them. You can also search through the examples database using specific keywords. And when you're done, you can return to your analysis by clicking on the analysis list. We've reached the end of this introductory lesson. Not all the powerful features of QUAKE have been used or discussed during the lesson. Specific details about each command are given in the online help and in the supporting documentation for QUAKE. Thanks for watching.